Hi everybody, Dr. Pingle here. We are going to talk about a notebook in which we're going to use real data, in this case county health rankings and county election data. Both of these date from 2016. And we're going to go through this notebook and try to build a model that, as best as we can, predicts the outcome of the 2016 election results by county. So let's take a look at the notebook and see where we start. So many of these import statements at the beginning should look familiar to you. We have a block of import statements here, importing pandas and NumPy and Matplotlib standard tools. We're also importing Seaborn, which is used for data visualization, although we're not actually going to be using that in this particular notebook. If you don't have that installed and it's not importing, you can comment that line out. But we're also importing a couple of different pieces of stats models. So this is what we're going to be using to run our regression models. There are a few different ways to do this in Python, but this is my preferred way. And then especially for graduate students, we're going to be using a couple of tests, actually just one test of normality. In this case, the Wilks-Shapiro test from SciPy Stats. I've imported a couple of other ones here, the Jark-Barra test and the Lilliefors test. Sometimes I'll use those. There are plenty of these different kinds of tests of normality. They generally give fairly similar results on large data sets that we're likely to use. All right, so as we begin, we're loading in some data. This is data that we've used in class before, and we're loading it from the online GitHub repository for the class. So the first line just loads in the election data, and the second line loads in the county health rankings data from 2016. Other years are available. If you want to combine years, if you want to use multiple years, you can certainly do that, but that's not necessarily required for this assignment. And then we on line 10 here, we combine these to form a single merged or joined data set with all of that information in the same data frame. I've got a line here. You'll notice that as is common with this data set, there are spaces in the file names, in the column names. This makes for very easy to read column names. It does sometimes complicate the construction of statistical models, just because, well, Pandas has syntax that sort of facilitates spaces in column names. The sub-language that's responsible for creating the models in our regression models doesn't always handle spaces very well. So we're going to do a workaround with that. But I wanted to at least demonstrate here what some of these options are. If you have spaces in the file name, or in the column names rather, it's quite easy to change that. So you can see that this line of code would replace all of the spaces in all of the columns with an underscore. We're not going to execute that line, so we can leave it commented out, but I thought people might be interested in that moving forward. Certainly the thing to do is to not loop through your data and fix it manually. All right, so I'm actually going to restart and clear the output here. This is more like what you'll get when you download the notebook anyway. And we're going to just go with these import statements and then prepare the data. So we can see what it looks like here. We're just looking at the first 5 lines with head. You can see that we've got FIPS codes in states and counties, and all of our information here on the left is county health rankings data, and then on the right, a lot of our election data. And you've worked with both of these before, so none of that should look very new. And then we're just using a print statement here to take a look at the column values, basically just a big list of these, because we do have 162 columns. You can't see them all because it's suppressing the output here, because that would be kind of unwieldy. So just printing these out to the screen here, just so you can sort of see what's in here. Now, the objective of this notebook is to build a predictive model to try to guess the election results by county based on any of these parameters. All right. So again, you've looked through these, but refresh your memory. There's a lot of stuff in here. All of these, I'm sure you could make sort of a mental case of like, why might this be related to the election results? And probably all of these are a little, right? We've talked about the fact that any variable can partly predict any other variable, even if the correlation is 0.001. There's still a hair of predictive value there, right? Now, if it's a bad fit, that's essentially what's called overfitting the data. You're using a data that doesn't really necessarily correspond, and you're using it to predict another. But just know that mathematically, every variable will contribute some, even if it's tiny, some ability to predict. But that may be a spurious prediction. It may not matter. So your task here is to look through this list and not to sort of pick randomly off of this list, and not to just sort of guess, but to really think carefully and not just about which of these things are likely to really be good predictors. It's okay to be surprised and it's okay to be wrong, but what I don't want you to do is to be haphazard about your selection here. So part one is about transforming your data. So we're going to start with essentially what you're being asked to do is explore 10 different, so here are your instructions. You're going to explore 10 different likely contributors to the prediction model. And we're going to be working through transformations on that data to try to get the most value out of it that we can. And I start with 2. So you can leave these in the table, that's okay. So you're 20% of the way done with this problem right from the beginning. Your objective is to start with these, and so my advice is to just use what we've got here and fill them in on the table here. So we're going to start with the demographics of population, and that is going to go. It's actually already here, but that is going to go right there. So be careful as you do this. This line of code essentially goes into the data frame. It pulls it out and stores it as X. And while it does that, it's dropping any of the missing values from the list. The next bit here is doing a particular transformation on this. And so I've left it here as a log transform, but you can see that there are a couple of suggestions here for how you can do it. Now, you're going to have to explore different transformations of this. You should certainly try a log transformation, but you may also want to try a sort of a more arithmetic transformation here. So in this case, we're taking the log of x. So what e to the e to the what equals that value in the data set. So that's a log. Otherwise, we can add and subtract things from the data. We can raise it to exponents. The adding and subtracting is really just about sort of recentering the data. If that doesn't make sense, it'll make more sense as we try out a couple of these things. So let's start with the demographics here. Population. The idea here is I might really expect that a county with a large population often is more likely to vote Democrat than one with a smaller population. So we're going to use that. And we want to take a look at this data. So all we have to do is execute this code block here. And what we see on the left is our untransformed data. And what we see on the right is the transformed data that we've transformed like so. So this is the natural log of the population data. Now I wanted to start with this because this is actually really typical of geographic data. It's just hugely bunched up here, right? If you think about all the counties in the United States, how many counties are small versus how many counties have large populations. So notice that this is scientific notation. So 1E7 is 10 to the 7th. So 1 million 1 million or 10 million. Big, right? So, so you can see that we have a lot. We have almost 3,000 counties in this lower band here. And then we have just a couple really large ones, right? There are only a couple counties that are really big. So, does this data need to be transformed? It totally, definitely does. It's got a really strong, what's called a right skew. Whether it's left or right skew depends on how long this tail is. If you do not remember information about skew, what you want to do is maybe just kind of refresh your memory. I put a link here, plenty of other stuff to look at online as well. This has a strong right skew. So we've talked about in class a number of times, the easiest way to deal with this, where things get kind of bunched up over here, is to do a natural log transform. So log transforms are useful when the data values are positive and the data values are skewed right. We're meeting both of those criteria. The data values are positive. Population is always going to be a positive number. It should never be 0. I suppose that's theoretically possible. You could have a county that's empty. I don't think that any counties in the United States are entirely empty. So, we apply the natural log, and what we're showing again here, this is the untransformed data, this is the transformed data, and what we're looking for is kind of a bell curve shape. So we decidedly do not have a bell curve shape here. We come pretty close to a bell curve here, right? So this is totally reasonable. And so what we want to do is we want to add this into the table. And as I said, I've started this for you, and you're going to add to this as we go. And I'll do one more in here that I don't cover here, so you can see what the adding process looks like. But I've already entered this in here, so you're going to fill this in. What's the untransformed skew? As we said, this has a strong right skew, right? It's not just leaning a little bit, it's totally leaning. So strong right skew. And then the transform that we want to use is a log transform. All right, we meet both of these criteria, so that's a good idea for us. For graduate students, keep in mind here that whether we get to a bell curve or not, it's actually pretty easy to diagnose visually. There are some statistical ways to look through this. They don't actually always work as well as eyeballing it. So even though there are statistical tests of normality, I usually don't trust them. I may certainly report them in the write-ups and the analysis that I do, but most of the work that I do to try to achieve normality out of a data transform is just visually. So in this case, we're using the Wilks-Shapiro test, which is one of a bunch. The untransformed data, we're getting a p-value off of this that's being reported as 0, but that's actually just infinitesimally small. What that's telling you is we fail to reject the null hypothesis that this is, we reject the null hypothesis that this is normally distributed. So definitely not normal. This p-value is under 0. This is definitely not normal. It's close to 0. This one though is also, to the eye looks relatively normal. The p-value for this is also quite small. Keep in mind that this is not 1.34, it's 1.34 times 10 to the negative 12, so that decimal point moves leftward 12 places. The Wilks-Shapiro test is essentially telling us that this one's not normal either. And that's fine. And undergraduate students, you don't need to pay any attention to this at all. But graduate students, I'm putting this in here just so you can sort of see how the data, how these sort of tests of normality respond to what you're seeing. So, so we would fill in a strong right skew up here. So we've done that already. I've double-clicked into this cell. This is a markdown cell, and this is the way that you would format a table. You don't need to get, so essentially what we're using is these vertical things called pipes. So this is the key that's above the backslash. If you shift backslash, it's usually right above your enter key. So that vertical line essentially divides up columns, and then these dashed lines create the separate the header row from the data, and then we just put pipes in here. Now you don't have to space these out. You can see that I have not spaced these out. The beauty of this is it'll do all this for you. So if you run this markdown cell, it'll format this into a nice table for you. All right, so let's take a look at the second one. So the second one that I've done here is GOP minus the Democrat percent from 2012. So the idea here is I want to be able to perhaps predict the 2016 results from the 2012 results. So we're going to fill that in here. So again, we're pulling this out of our data frame and we're storing it in a variable called x. We'll just run this again as we did before. So on the left again is the untransformed data. Does this have a skew to it? A little bit. It's got a little bit of a left skew, right? So the left tail is longer than the right tail. So it's a sort of a weak left skew. Transforming this data is probably not necessary. This is probably normal enough. But part of the assignment is to get you to sort of experiment with these things. And so let's experiment with different transforms that we could do to maybe make this a little bit more normal. Could we perhaps erase this skew just a little bit? So that's what we're going to try to do. Now, one of the problems with, so we've applied a log transform here, but we've actually made it worse, right? So now we have an even worse left skew than we had before. And we've also sort of disobeyed this point here, which is that the data need to be positive, and they aren't, right? We have negative values in here. So a log transformation is, you can't use that when you've got negative values. And a log transform is used when the data are skewed right, and our data is actually skewed left. So we don't meet either of those two things. We're actually making things worse by using a log transform here, and so we don't want to do that. So instead, we can use an arithmetic transformation and kind of play with that a little bit. So one of the things that you can do is you can take x and you can put an exponent on it like this. All right, so we're taking the x value and we're squaring it. Is that going to make our data more normal? Definitely not, right? We've made things worse. It's right skewed now instead of left skewed, but it's definitely not anything like a bell curve. And if you think about it, squaring these things is going to take all of the stuff that was on the left-hand side of this, and it moves it onto the right-hand side. Anytime you're doing a data transformation, it's really important that it's invertible. So you can go back and recover the values. And because you've got negative values here, when you square it, after you square it, you don't know the difference between negative 25 and positive 25. You're going to get the exact same thing. So, so one thing that you can do to sort of preserve that is to do a shift of the data all positive. And so one of the things that we can do to make this all positive is we could add 100 to it, right? Because our data can't be less than 100. So by adding 100 to it, we're going to move all of the negative values to the right, but in a way that's, again, recoverable. At this point, no matter what answer we get, we can go back and sort of figure out what our original answer was. Now, when we do that, we wind up with a value here that's, we've gone from sort of a left skew here to a right skew. We've transformed our data, but we've probably gone a little overboard when we did it. And so do keep in mind that exponents can actually be fractions. So this would be taking the square root of that. And so you can see that we've actually, again, made our data a little bit worse. It was left skewed. Now it's more left skewed. If we do this, we're not really using an exponent at all. And so that still has a left skew to it. In fact, this should look exactly like this one, except for that it's just moved over. And so we can basically add exponents to it until we figure out something that's a little bit more bell curve shape. So this is kind of in the right direction. This is a lot more like a bell curve. It doesn't sort of lean like this one does. By the time we get to 2, though, it's starting to shift the other way. So our number in here is sort of sensitive, right? Now, whether we use 1.5 or 1.4, both of those are sort of look pretty good. We could certainly keep 5; that would be fine. But by the time we get to like 1.8, you can see that it's already starting to lean. We now have more of a right tail than we had before. So you're going to sort of play around with these values. On a lot of the ones, how this works out will depend on the data. If your data comes in as a percentage between 0 and 100, you're not going to need to add anything to it. If you've got negative values, then you're going to need to shift those. And what these two values are, what you're adding to it and what your exponent is going to be entirely dependent on your data. So play around with those numbers to try to get something that looks a little bit more normal. And my intent here is to get you to play around with this and to sort of turn knobs. And if I do this, what happens to my distribution? And if I do that, what happens to my distribution? There's, so anyway. Now I said I'd do one more so you could sort of see what it's like to add to this table. I'm going to pick one that Richard Middleton actually is really very fond of. So we'll do sexually transmitted infections. The chlamydia rate, is that predictive of the election? Richard Middleton says that it is. Let's find out. All right. So we've got data here that's strongly left skewed, right? So just like we had before, we've got a strong skew here. We don't have any negative values, so we don't have to worry about that. We don't have to worry about that, but we have a strong right skew. Easy to get those two mixed up. Strong right skew and no negative values. So this is actually a good candidate for a log transform. So we'll just put that back in here. And sure enough, we go from something with a pretty bad right skew to something that's pretty nicely normally distributed. So we're going to fill this in on our table. We'll copy my variable name there. We've got a strong right skew, and then the transform that we think is probably going to work really well is a log transform. Right? And again, that's true because we meet both of these two criteria, and visually we can see that it did do a pretty good job of leveling that out. So when you get done to the end of this, you'll have 10 of these. Just try to pay attention to the formatting. So there's sort of a pipe on the left, pipe, sort of defining the column boundaries of your data. And if we run that, it renders that as a table. And so when you're done, as you're working on it, you'll kind of leave it in this state. But when you're done with it, then you're going to run that markdown block, and it's going to turn into a nice looking table. I would like these things sorted alphabetically. So in this case, this is already sorted D, G, S. But if you need to move something around, you can just copy and paste things, and it'll just move it around that way. So you are going to need to do it manually, but it shouldn't be too hard with just 10 of these. All right, part 2, testing variables one at a time for an R-squared value. So based on the values that you get up here, you're going to run this code block with those things in it. You're going to leave this alone, right? This is what you're trying to predict, the 2016 data. But what I want you to do is to run. For each of your 10 variables here, you're going to run it once untransformed and once transformed according to how you made a note above. And probably a lot of these are going to be log transforms. And you're going to report back the R-squared value for the untransformed data and the R-squared value for the transformed data. So let's start with demographics and population. So you're just going to plug that in for the X value. And again, we want to run this transformed and untransformed. So we're going to start with untransformed. We run this code block, and all we're doing is we're running an ordinary least squares regression using our X variable to predict our Y value variable, and we're pulling out this R-squared value. So my R-squared value for demographics here is 0.123. looks like we've got an error in here anyway, so 0.123. And then we want to run the same thing again with the transformation that we did. So we're using a log transform. So we say np.log of our variable. And this time we get a value of 0.0255. So we're going to put that into our results. All right, let's run this data. All right, so we are first just going to paste this in here. And run it. And we get a value here of 0.891. So that's a strong predictor. That's almost 90% of the variance is explained just by how people voted last time. So we'll paste that in here. And then our transformation for this one, excuse me, our transformation for this one is x plus 100 to the power of 1.4. So we are going to edit this. So plus 100, and then to the value, or to the power of 1.4. And here we get a fit of 0.87. So using this transformation actually made things a little bit worse. So we would not really want to use a transformation on this. We would want to keep the original values. But this is about sort of just trying these things out. So those are the two that we kind of started with. Let's take a look at the third one that we did here. So this is the chlamydia rate, and our transform is just a simple log transform. So we'll start off here. We'll get rid of our transformation and execute that block of code. So here, chlamydia is responsible for 23%. It's a stronger predictor than the demographics. So let's put this in here. And I would like these things ordered from most explaining to least explaining, but you can do that at the end. So there's the chlamydia rate. Our untransformed response was 0.023, and then our response with a log transform looks like this, 0.099. And then at the end here, there's just a rationale that I'd like you to include. Why do we think that this might be a good fit? We can put anything we want here. That might be true. I don't know. Maybe like health issues might relate to votes. Whatever it is that you think is a better response here. Feel free to fill in here. And it is nice to have pipes at the end, although you can see that actually it didn't make a difference for how the table rendered. So, very forgiving syntax. All right, so you're going to do that for all of the 10. And again, when you get to the end, what I'd like you to do is sort of order these from most explanatory power to least, where the sort of best score for that line. So this one, the best score is 0.89, so that's at the top. This one, the best score is 0.25. 0.255. So the demographics is just a little bit of a better, when transformed, is a bit of a better explanation than the chlamydia rate. So this is now in the right order: best score, second best score, third best score. All right. So in part 2, you've gone through and explored how different variables individually explain the results. In part 3, you're going to explore some interaction effects. So what I'd like you to do is to pick 3 of these things up here. You're going to have a list of 10, remember. I've only got a list of 3, so that's what I'll use for my model here. But you'll use 3 or 4 to make your model. So basically, what you're going to do is fill these in here with the variables that you've chosen. And you are going to look and see. So that's all that one takes. Okay, so we pasted these in here, and sorry for a bit of a hard jump cut here, but there was a bit that I had recorded that I had to re-record. Now we pasted these in here, and we can run this and get our results back. However, what I did want to do was make sure that any transformation that we've done up here that we thought made sense, we want to do down there. So essentially what we're looking for is we want to use the highest R squared value for that variable, whether it's untransformed or transformed. So the previous vote, the 2012 vote, the best result was actually when it's untransformed. The demographics, the best result was when it had a log transform. And the chlamydia rate was most effective untransformed. So that's what we want to do here. So essentially the only one that we want to do is a log transformation on the demographics because that's the one that had a higher R squared value, and we had the kind of transformation was up here. And again, we've had to kind of it's a bit of a jump cut here, but hopefully this makes sense to people. So now that we've defined our models, we can run that. All of these things here, essentially the asterisk means that we are testing not only the interaction of A and B, but the interaction of A and B. So this is going to test the interaction of 0 and 1, 0 and 2, 1 and 2, and 0, 1, and 2. And you can see that all of those are down here. So we could take a look at our p-values for all of these. And in fact, our p-values are all below 0.05. I've created a table up here where you can essentially evaluate whether these p-values are less than 0.05, in which case the result is significant, or greater than 0.05, in which case they're not significantly significant, statistically significant. And so if we look at x0, the p-value is listed here as 0. That's less than 0.05, so it's significant. We look at x1, again, less than 0.05, so it's statistically significant. Remember that they're never really 0. They're actually just too small to report, less than 0.0001. So in fact, all of these are significant, so we would paste these here. I will show an example of something that works out not statistically significant so you can see. But if we had not done this transformation here and had executed it, what we would find out is that the interaction now between the GOP 2012 and the chlamydia rate comes back as not statistically significant. So interestingly, by not doing a log transform, we actually affect the other two variables. That's an important thing to keep in mind. You can have variables that are what are called strongly collinear, meaning that the variables themselves are related. Generally, we want to avoid having redundant collinear variables in a regression. If variable A pretty much captures variable B, and those two are correlated, then you don't want them both to be in your statistical model, like trying to predict variable C. Whether that happens or not, again, I want to, that gets in a little deeper. It's an important thing to look for. Graduate students should certainly be on the lookout for that. But undergrads, probably sufficient to know that it's generally to be avoided. An example is if I was predicting height to predict weight, I wouldn't want my height in inches and my height in centimeters to both be in there because those two things are obviously perfectly correlated. We would only want one of those things in there. So, all right. So this is our model. What we actually want is this. So we'll put it back in here. And so these are our results, and we put those results into the table. Now in part 4, you're going to have these same variables that you've got here, right here, so you can copy and paste those. And what you're going to do is you're going to express this model using only variables here that are statistically significant. In this case, I've written them as if we hadn't done the log transform here. So I had removed the x0 by x2 interaction term. So these are all of my base variables, and then this is the interaction between the 2012 vote and the demographics. This is the interaction between the chlamydia rate and demographics. But there was no term for 0 and 2 because, as I just demonstrated, without this log transform, that one's not significant, so I could just remove it. Now, because so only keep these items that are statistically significant. In this case, I could add this back in and put x0 interacting with x2. So this would be a complete model, and I could run this. But I could also use the same shorthand that I used up here. Since all of these worked out, I could simplify that a little bit. Again, all of these variables are significant. That shouldn't be surprising. I'm running the exact same regression in this case, but yours may not work that way. It's very likely that at least one of your terms will not be significant. And then finally, you're going to write a section here where you're running a contingency table or confusion matrix to try to see how well you did in predicting your results. So in this case, we are doing a little bit of just doing a binary comparison here. The true values were how the vote actually came out in 2016, but wherever those values are over 0, in other words, wherever Republicans got the preponderance of the vote, we'll put a true, and if Democrats had more votes, then it's false. And we do the same thing with our predicted results. And notice that the results object that we get out of our OLS can do more than just print a summary. And here we're actually pulling out those fitted values, meaning we're using the predictions that come out of that, and then we're doing the same sort of binary Republican-Democrat filter. These two lines of code just remap those from true-false to R and D for Republican and Democrat. That's always a nice thing to do. It's not strictly necessary for the math, but it makes looking at it and interpreting a table much easier. So you don't have to modify any of this code. You should just be able to run it straight, but you're going to get an output confusion matrix here. So I predicted 451. So if you do a column total of this, that's the number of Democrat victories that I predicted. Republican victories would have been 2,487, right? So summing that column. But I was correct 400 times. I predicted 400 Democrat victories, but I was wrong in 51. I was right in 400 cases, and I was wrong in 51 cases. And Republican counties, I was wrong in 85 cases. Mostly a good job here. The second bit here is using a normalization so that I can get the percentages. And when I do that, I get percentages that look like this. So all of these should add up to 100. And so you can see that there were a lot of correct Republican predictions. Why so many? Remember that there are a lot of counties, a lot of small counties. Democrat counties tend to be larger. Republican counties tend to be smaller population-wise. But there are more of them. So that's sort of why these numbers turn out the way that they do. So the total correct is going to be this 13.6% plus 81.7%. And so from the zeroth row, 0th column, so that's here. The first row in the first column, that's here. I add those two together and multiply by 100, and that's my total victory percentage. So I'm right 95.37% of the time with this particular model. All you should have to do for this section, though, is to paste in your values above, making sure that you're using a transform here as appropriate, and then these are the, and including only the interaction terms that you need. I'll leave this alone, but this would have worked equally well. All right, and I should get the exact same values. Right. This is just a simpler syntax for the model that we just had. And again, I'll put that back because it might be helpful for you. Okay, the final bit here, I'd just like you to write a paragraph here in Markdown explaining what you learned about regression and about predicting the 2016 election results. I'd like you to name 5 more variables not included in these data sets that you think might be helpful in predicting the results. I've got a statement here that says these variables should be operationally valid, meaning that one could easily imagine that such data exist. I don't want you to just sort of pull things out of the air. I want you to think about what variables might actually exist that could go into this model. As an example, if we're trying to predict the 2016 election results, knowing the 2014 midterm results might be really helpful. And for those of you listening to this video, you're welcome to include that as one of your 5. But think about whether that thing is likely to exist. You don't have to know where it is. You don't exactly have to know where you get it. But do give some thought as to whether or not such a thing is likely to exist. Don't just put down random things here. Again, the purpose of this assignment is not to get you to just pick random things off of a list and turn the crank on a regression. I really want you to think about what's going into your model and why you're doing this transformation, why you're including this interaction term. And your answer can be, it makes a better looking histogram. It looks more like it's normally distributed. It has a p-value of less than 0.05, but you need to know what those justifications are as you go through. And then finally, when you're turning this in, you're not going to turn it in as a Jupyter notebook. This is the first notebook that we should be able to use the notebook as PDF. Bit that we installed when we installed this environment. So you're going to go to File, Download As, and then PDF as HTML. And it's going to use that package that we installed when we installed the Analysis in GIS notebook. And it's going to render this out as a PDF. And that PDF is going to look like this. And so you're going to turn that in with your, you're going to turn this in as your assignment rather than the other. So thanks for listening. Good luck with the assignment. I hope you found this walkthrough video helpful, and definitely come to me or the TA if you have questions. Thanks very much. Bye.